Hi, my name is Marius, and I have spent this summer of HPC at the Cypress Institute, trying to enable Lattice QCD simulations on GPUs. So, what is QCD? Well, in school you have been taught that an atom is made of electrons, protons, and neutrons. And while you can split the atom itself, these particles happen to be elementary. Unfortunately, this only happens to be true for electrons. Protons and neutrons are compound particles as well, and made of quarks, which bind together really strong, doing so by means of a strong interaction. This interaction is described by quantum chromodynamics. Chromo, because it's transmitted by 3 color charges, instead of, for example, the one electric charge of the electromagnetic force. So, how do we calculate this? Well, first we have the fermionic action. Quarks are fermions like nucleons are, which looks like this. Then, we also need to consider the gluonic action. Gluons are the interaction particles of QCD, like photons in the electromagnetic force. So, the QCD action is a sum of these. Then, you can measure an observable, like in any quantum field theory via a path integral. Looking at this, you might realize that this is nothing you want to solve on paper. In fact, there isn't even an analytical solution to this. Even perturbation theory fails to work here, since the coupling constant is too large. So, what should we do? Well, we now get to simulate the whole thing on a 4-dimensional spacetime lattice. To do so, we start by setting all the fields to random numbers, and then letting them evolve according to the equations from earlier. We do this step by step, to get something we call a trajectory or Markov chain of gauge configurations, which then can be used to run some measurements. We take the whole chain for this, since the single configurations tend to be a bit noisy. So, what did we actually do to speed up the calculation? Well, the most expensive part happens to be the inversion of the Dirac matrix, which is thus enormously large. It includes the interactions between any 2 points on the lattice. Luckily, we can apply a little trick here. The inversion is done by conjugate gradient algorithm, which runs faster for large eigenvalues. So we simply rescale. This had of course already been done in TML-QCD, the lattice QCD package used by the group here in Cypress, but the calculations could not be done on GPUs yet. Additionally, this trick adds some new parameters, which need and have been tuned to make the code run properly fast. So, how does our code scale with the number of available GPUs? Well, pretty bad for small lattices. There's even a dip at edge GPUs since we have to open up a new MPI dimension here. But lo and behold, we have larger lattices. For a medium size, this already looks pretty good. And for an even larger size, we can see a little more improvement, but unfortunately, this one was not divisible by 12 GPUs anymore. And last but not least, our measurements. We took a look at pion correlators instead of protons, since they happen to be the most easiest to calculate. And of course, these correlators should not be at the order of 10 to the 4, this simply is a normalization factor missing somewhere. So, if we have the correlator, we can perform a simple exponential fit to extract the pion mass, which gives us about 260 MeV. Now, if you look at the actual pion mass or look it up, you will notice that this is not that close to the physical 140 MeV. But this is fine, since we were using a larger than physical quark mass to begin with, and that way our result is about what we expected. So, I hope you enjoyed this video as well as I did my summer, and see you around Europe.